Chairman, dear colleagues. My name is Alexander Zakharov. I represent the Kazan Scientific Research Center of Russian Academy of Sciences. And the present study was performed by leadership of Professor Shlyalnikov, and Dr. Anastasia Gerasimenko also participated in this study. So let me introduce you the outline of my talk. You can see that the present study can be divided on three main sections. The first one will be an experimental study of surface crack propagation in cruciform specimens under biaxial loading. Then I would like to talk about numerical calculation of in-plane and out-of-plane constraint parameters along a crack front in cruciform specimens. And then the last part of my talk is concerned with crack growth rate interpretation. Some words about motivation. Fatigue crack growth rate study is one of the most important elements in structural integrity prediction for structural components with accumulated operational damage. In most cases, operational damage that appear on the free surface of structures are approximately considered as a semi-elliptical surface cracks. And biaxial loading conditions are typical for the metallic components of engineering structures, such as turbine disc, airplane fuselage schemes, pressure vessels, and so on. So the problem of predicting the residual fatigue life of such type of structural elements is complex. And the actuality of this problem is evident. So, in this study, experimental results for fatigue surface crack growth in cruciform specimens under biaxial loading are given. Distributions of governing parameters of elastic plastic stress field along a crack front in cruciform specimens were obtained by finite and method numerical calculations. And on this base, the crack growth rate diagrams were given in terms of new plastic stress intensity factor. The subject of this study are cruciform specimens with surface cracks. Surface crack growth study was performed for equibiaxial tension, biaxial tension 0.5, uniaxial tension, and equal biaxial tension compression. All tests was performed for aluminium alloy D16T, and its main mechanical properties are listed in this table. The fatigue crack growth rate tests were carried out with servo-hydraulic biaxial test system at room temperature with sinusoidal loading form at frequency 5 Hz, and the stress ratio R equals 0.1. And both optical microscopy and crack opening displacement method were used to monitor the crack propagation during the test. And in order to fix and highlight the crack front positions as a function of accumulated numbers of cycles of loading, several benchmarks were produced by increasing the stress ratio from 0.1 to 0.75 with a constant value of maximum cyclic stresses. In this figure, you can see the experimental results, experimental crack front positions as a function of accumulated numbers of cycles of loading. And these results show that fracture process in cruciform specimens can be divided on two parts, in two stages. On the first stage, crack propagates like a surface crack, semi-elliptical crack, and on the next stage, surface crack completely crosses the specimen thickness, and then crack propagates as a full thickness crack. So on the basis of these experimental results, we obtained the relationships between aspect ratio and the crack depth. On this figure, you can see the experimental data obtained by direct measurements of crack length and crack opening displacement. This figure represents the relations between crack opening displacement and crack length on the free surface of specimen. And this figure represents the dependencies between crack growth rate on the free surface of specimen and the crack opening displacement. And you can see that in the first stage, when the crack propagates like a surface, semi-elliptical crack, there is a significant influence of type of biaxial loading. So that was experimental results, and now we talk about numerical calculations. Numerical calculations of present study are concerned with stress-strain analysis along the crack front in cruciform specimens for all considered types of biaxial loading, into account the in-plane and out-of-plane constraint parameters. And on the basis of solutions for governing parameter of elastic-plastic stress field along the crack front in cruciform specimens, we calculate the plastic stress intensity factors for the crack growth rate interpretation. Finite element analysis will be performed for both surface cracks and through thickness cracks. So you can see the typical finite element models for cruciform specimens. And for representation of our results, we used dimensionless coordinates. In case of surface crack, we used a dimensionless angle P. And in case of through thickness crack, we use a dimensionless coordinate Z normalized by thickness of the specimen. In this figure, you can see the distributions of in-plane T-stress parameter and out-of-plane TZ factor along the crack front of surface floor. These distributions of constraint parameters presented for the two positions of surface cracks with aspect ratio 0.3 and aspect ratio 0.6. In this figure, you can see distributions of stress triaxiality parameter and governing parameter of elastic plastic stress fields, IN factor. It should be noted that all of these constraint parameters has are significantly changed along the crack front, and as well as they are function of loading biaxiality. In case of through thickness crack, constraint parameters also represent for two crack front positions that are determined by equivalent crack length 0.35 and 0.7. So we can see distributions of T-stress and TZ factor. And then in this figure you can see the distributions of stress triaxiality and IN factor. And with compare of surface cracks, parameters T-stress, TZ factor, and stress triaxiality has a more uniform character. So, as mentioned above, on the basis of solution for IN factor, we calculated the distributions of plastic stress intensity factor along the surface crack and along the surface crack front and along the through thickness crack fronts inclusive of specimens for all considered types of biaxial loading. So these numerical results were used for crack growth rate interpretation. So let's come back to our experimental data of crack propagation in cruciform specimens under biaxial loading. So you can see that there is a strong correlation between crack opening displacements and crack length. And these relationships between aspect ratio and crack depth as a function of crack opening displacement is very useful for automation by experimental study for surface crack growth. And utilizing these relationships, we calculate the crack growth rate in the depth direction. So, as a result, the crack growth rate on the free surface of the specimen and crack growth rate in the deepest point were introduced in terms of plastic stress intensity factor. And I would like to pay your attention that for the first stage of fracture process in cruciform specimen, crack propagates, crack growth rate significantly increase in a small range of plastic stress intensity factors. And in the next stage, a significant reduction of crack growth rate is observed, and crack growth occurs in a wide range of plastic stress intensity factor. So I believe that this result demonstrates the advantage of plastic stress intensity factor application as a characteristic of fracture resistance material properties. And crack growth rate diagrams in terms of plastic stress intensity factors in this study was introduced as a generalized diagram in normalized coordinates. So you can see that experimental data for different types of biaxial loading remain the narrow scatter band, and such a generalization can allow us to obtain a single curve that describes a strong correlation between crack growth rate and plastic stress intensity factor. So, the conclusions of my talk. Fatigue surface crack propagation in cruciform specimens from D16T aluminum alloy under biaxial loading was studied. Experimental results showed that biaxial loading lead to main stage for cyclic fracture process of the surface crack. The experimental and numerical results of present study background provide opportunity to explore suggestion that crack growth rate may be represented by the plastic stress intensity factor rather than the magnitude of the elastic stress intensity factor alone. The fatigue fracture diagrams in terms of plastic stress intensity factors was introduced as a generalized diagram in normalized coordinates. And generalization of typical crack growth rate diagrams in normalized coordinates provides a single curve that describes a strong correlation between crack growth rate and the plastic stress intensity factor for different loading conditions. So thank you very much.